Thank you, Lisa. Thanks to you and your staff at the museum here. This really is a wonderful partnership between the Boston Museum of Science and La Fondation Wright in Geneva. That's the Wright Foundation in Geneva, Switzerland, the parent foundation of the Wright Center at Tufts University. This has been an ongoing series on this side of the pond for some 12 years now. We do this series in the odd years in Boston and in the even years in Europe. So if you miss the series in Europe, you can't get to Geneva, just look next fall on the World Wide Web. So welcome to all of you who are just joining us for this talk tonight. Welcome to those of you who have been with us in the previous nights, and again, welcome to those of people who are viewing on the internet. We've been attempting to address the scenario of cosmic evolution, as has been the case throughout this series. We're moving across the archetypical symbol, as I understand it, the arrow of time. We're placing the emphasis on change and on testing. Change because when we look out the window, as Heraclitus did 25 centuries ago, he noted that in probably making the best observation anybody ever made, everything's changing. Whether it's galaxies, stars, planets, or life forms, as we now understand it, a good deal more than perhaps he would have understood. We're trying to place meat on the bones of his skeletal idea. But we as scientists are demanding that these ideas be tested. We're demanding that the ideas be observed and examined through observation, through experiment, and the like. That's the scientific method. That's the central dogma that we have in science. We believe, as scientists, that neither thinking alone nor belief alone will ever make the unknown known. We just demand the test. And by testing and deriving and accumulating more and more empirical evidence, we can hopefully discriminate in an objective way over the course of time between what is sense and what is nonsense, getting rid of the nonsense as quickly as possible and accumulating more and more of the sense as we move progressively, and I think there is a progression there, toward a better and better approximation of reality. So it's an interdisciplinary, integrated story that we tell over the course of Big Bang to humankind. It's an attempt to examine change, physical change, biological change, cultural change. It's a story that ramps up from quarks to quasars, from microbes to minds. In effect, we're trying to build a cosmology here, a cosmology now in which life has an integral role. So we've used this one symbolic form here, this arrow of time, as a one-page summary of where we're going or where we've been. 2 weeks ago, we had a couple of wonderful speakers here, Frank Wilczek and Colin Norman, speaking about the early universe. Were there gaps there? Oh, boy, there are a lot of gaps. A lot of missing links thus far, especially in the early universe. They gave a couple of wonderful talks, but we came away, of course, severely uninventoried. Lots of dark matter, lots of dark energy. We discussed that 2 weeks ago and last week as well. In fact, last week we had another two wonderful speakers, Mike Shire and Dimitar Sazlov, moving us further along the arrow of time and examining the stars and planets. And we didn't agree on a whole lot last week other than the fact that all three of us, I think, did agree that Pluto, it's time to demote Pluto as a planet. So that probably explains this week why I'm starting to get some hate mail from those third graders. And next week we'll push along the arrow of time further, not toward any culminating or pinnacle of cosmic evolution, but we'll reach the here and the now, and we'll have Fred Speer here from Amsterdam and Jill Tarter from Berkeley, the SETI Institute, speculating about how we ourselves have come to be as we are in this grand story of change in this scenario, and perhaps with the last speaker, Jill Tarter, to make a gesture to the unknown, to speculate where we might be headed as a civilization or as a species. This week we're in the middle part of the arrow of time. You might think that we're crossing the line between physics and biology, but to my mind, it's a longer story at another time perhaps, I don't think there is any line there. I don't think there is any line between physics and biology. I don't think there is any demarcation between inanimate and animate. We are moving toward greater and greater complexity across the arrow of time. In fact, that's going to be a central issue throughout this cosmic evolutionary scenario and in the research domain that extends well beyond these Wright lectures. Because you look out at the window of Heraclitus or whatever, you see nature and you wonder, how is there so much order, form, and structure? And how is it that order and complexity is increasing with time? Despite, if you were to push me as a physicist into the corner, put the bright lights on me, a little like there are now, and say, what is the most cherished law in all of physics, I would have to confess is the second law of thermodynamics, which prima facie would suggest that things ought to be breaking down toward greater simplicity. So can we reconcile the observed constructiveness of cosmic evolution, where complexity over the course of time, at least within islands of ordered structures such as stars, planets, and life forms, seem to be increasing with complexity, with the inherent destructiveness of the second law of thermodynamics. It's a longer story. It's another time. I think we can reconcile those issues. Tonight we bring forth before you then two world-class biologists. They will address the microscopic realm of science and of biology and the bigger macroscopic realm of biology. Our first speaker will address the microscopic domain. Lynn Rothschild is an expert from the NASA Ames Astrobiology Institute outside of San Francisco, an expert on microscopic forms of life, algae, protozoa, not only in an Earth-like environment, but in a larger planetary environment, should there be microscopic forms of life elsewhere. She is specializing largely in a wide variety of astrobiological issues, in particular the way in which radiation might harm organisms, a very, very important issue if we as humankind, as human beings, are going to try to move out now toward Mars. How does radiation, how does UV radiation react to or impact on, as NASA would say, using that word as a verb, on organisms? What does life do in extreme environments? She is a graduate, as an undergraduate of Yale, moving on to Brown for her doctorate. She is now a senior astrobiologist at NASA Ames, as I say, in California. She is an adjunct professor at Stanford. And I first met her at a little gathering a few years ago. We were talking at dinner at Windsor Castle when a number of us were gathered there together, and I think it was a late night evening discussion that she led, which I thought was so articulate that I resolved then and there in England a few years ago that I had to bring her here to Boston to introduce Lynn to this Boston audience and the right lectures. So please welcome as our first speaker, Lynn Rothschild from California.
Very, very kind introduction. And I wanted to say, being in Boston here, I grew up in southern New England in Connecticut, and I had absolutely no idea there were this many people in Boston not interested in baseball. So thank you, all of you non-Red Sox fans. I should say that I have a 6th and an 8th grader, which you'll see both of them in later slides, and even my 8th grader's English teacher takes days off for the Red Sox, and that's in California. So I say I'm particularly impressed that all of you are here. What I'm going to do, although my background's in evolutionary biology, the more time that I spend at NASA and thinking about life really beyond Earth, the origins of life, what life means and so on, the more I really go back to the future and back to, in some ways, the pre-Darwinian world where we're thinking very much about the physical environment rather than competition among organisms. So what I'd like to do is give you maybe a slightly different take on early evolution than perhaps you're used to from what you get in classes today, the sort of classes that my colleague is going to talk about and teaches. And so what I'm going to do is tweak you hopefully a little bit and talk about environmental controls on the evolution of life. So the only way to start this is in the beginning. We're going to cover about, 3.5 billion years in the next 30 minutes. So the answer is, hang on to your seats and fasten your seat belts and try not to blink. So let's start 4.6 billion years ago with the formation of our solar system. And at the center, of course, we have the sun, the source of most of the energy that organisms on the Earth ultimately use today. And at the same time, roughly, we had planets forming. Whether Pluto was one of them or not, I don't want to speculate, but we certainly know that Earth was one of them. The moon was not there from time dot. The current feeling on the street is that the moon formed when really a sort of Mars-like planet hit what was the proto-Earth. Some people call this Earth Mach 1, which is also roughly the size of Mars. It was an enormous collision. As I like to tell my students, it was the ultimate bad hair day in the history of the Earth. Enormous amounts of material were thrown up. Much of this material from this impactor was integrated into the Earth, and all this dust and debris that came up from the surface of the Earth coalesced. Some of it came back down to the Earth, and some of it formed what we see as our moon today. So that was about 50 million years or so after the formation of the Earth. Well, at some time later, we don't know exactly when, the Earth became heavily infested by living organisms. It may have been very quickly after this 4.5 billion year bad hair day when the moon formed. It may have been quite a bit later. We don't know. We do know from the fossil record that life was well established about 500 million years later. But there's increasing evidence that there was liquid water on the Earth almost immediately after the formation of the moon. This is an enormous surprise because we thought that there would be a huge period of time where the Earth would have to cool down before there could be liquid water rather than all of our water inventory in the form of steam. So it's possible that life arose very quickly. I've been sort of teasing my colleagues because they talk about huge amounts of time. They say, well, it takes 50 million years for life to form or 500 million years. And the answer is no one has any idea. And so I've been starting to tweak people and say, well, maybe it was a long weekend. Maybe it was Columbus Day weekend. You don't know for a fact. Maybe in a few years we're going to send our students home with a little kit on Friday and say, make the best life you can, bring it in Monday, and I'll grade you Tuesday. We don't know for a fact. But we do know that within 500 million years, the Earth was heavily infested with life. There's some cyanobacteria. What I'm going to do is sort of get you a few shots from the sort of field work that I do as a way to, take you out of the Boston area. These little fellows live in Yellowstone National Park, where we've done quite a bit of field work over the years. Those are cyanobacteria. They're our friends. They're the ones that are responsible for polluting the Earth with oxygen in the beginning. Okay, let's start sort of then from where we have this planet Earth. We have a moon, we have water, and we have some prebiotic chemicals. We don't know exactly where they're all from. We do know that we get organic compounds in water coming in even today from the solar system, from meteorites and comets. We know that a certain amount have been formed on the Earth. We don't know the relative amounts, but we're going to say we now have an Earth, we now have a moon, we have a sun, we have some organic compounds, we have liquid water, and we're ready to get going. So at that point, what you have is the prebiotic world. You start to have these compounds that are the building blocks of life, and we'll talk slightly more about them later. We then think there was some kind of RNA world, ribonucleic acid-based world. We think this because ribonucleic acids can both function as genetic material as well as enzymes. We now know that as well. It was worth 2 Nobel Prizes about 15 years ago. So say we have this RNA world that's encapsulated into these lipoprotein vesicles, not very difficult to imagine. Picture yourself making salad dressing, not ranch dressing, but vinaigrette. So you got the oil and the vinegar, and you shake it hard, and you got lots of little vesicles, and that's basically what your ancestors were dealing with. I don't really call this the vinaigrette origin of life, but I suppose you could think of it that way. Then from there, the fact is that RNA can do all these things, but proteins are so much better as structural elements. So I say that there was a protein coup. You can think of a great, overtaking of the RNA. The RNA was relegated to its other functions, and ultimately there would have also been a DNA coup. Deoxyribonucleic acid is double-stranded. It's much more stable. It's much better genetic material. But you see these traces of the RNA world through the cells. Okay, that's a very sort of simple, superficial explanation for the origin of life. But let's try to look a little bit more at what that might mean. And this is kind of an interesting thought. There's Carl Woese, who actually suggested this in a paper, although when I confronted him with it, he said, I didn't actually say it like that, but I'm glad you did. So I feel like I now have, at least his blessing to say this. That the very early cells then with this DNA material, RNA, and then ultimately DNA, were passing around. And, I'm sorry to say this in a very, serious, prestigious audience, but the fact is our ancestors were highly promiscuous. All this genetic material was being passed around. You didn't know who was who. You can think of it as sort of the rampant orgy origin of life. But at some point, there's some sort of thresholds being put down, some kind of idea of self, of individuality. And, maybe you don't want to pass around all your nucleic acids, all yourself to others. And so I think that this really is the origin of self, of individuality. And you start to pass your genetic material down to your offspring rather than sharing it with all of your friends, which no longer your friends, they're your whole family. And so from there, we start to think this point of having this great diversity of life. There are lots of microbes, there were dinosaurs, there are plants, there are animals. We have this marvelous diversity. And we could just sort of leave it like that. But now I want to try to put this a little bit in a physical context. And when we say a physical context at NASA, we're not talking about another 2 degrees global warming or, you know, the sun coming up 2 minutes later. We talk about major factors at NASA. We're sort of these grand, you know, grand thinkers or grand nutcases or however you want to think about it. This over here represents the sun. I don't think anyone here will have trouble recognizing this, but I know in some places that I've lectured where they haven't seen the sun for a while, I've had to point this out. This is the sun. Many of you will recognize it as our closest star. The sun is tremendously important to us because it gives off radiation. PAR is just a short term that we biologists use, meaning photosynthetically active radiation. In other words, the radiation that we see as visible light that the plants are able to use for photosynthesis, tremendously important. And the sun also gives out ultraviolet radiation, among other things. These are the two main things that reach the Earth. Now, the sun is a star. Stars burn. As things burn, they become hotter and hotter. So if you take the time and go backwards, if you run the clock backwards, we think that when the Earth formed and when life began, the sun was about 70% as luminous as it is today. So 30% less sunlight reaching the Earth. However, we do know from studies of other young stars that proportionally they put out more ultraviolet radiation. So where it would have been dimmer, the amount of ultraviolet radiation coming out to the Earth may have been roughly what it is today. Now, radiation has to make it through the atmosphere before it gets to the Earth, and our atmosphere was significantly different. If we think that we have problems with an ozone shield now, the Earth was one giant ozone hole when life originated. So much of this ultraviolet radiation and photosynthetically active radiation was making it right through to the surface of the Earth. What we had, we think at the time, was really a carbon dioxide atmosphere. We had a situation, particularly for a couple 100 million years, where we were suffering huge numbers of impacts. The lunar forming impact was the worst of the bunch, but that doesn't mean that it was a whole lot better. These impacts may have been so severe that the Earth could have even been sterilized several times. Hey, maybe life arose on Earth several times and was killed off by giant impactors. Unfortunately, there's no way we're ever going to be able to know, but it's a rather interesting thought. Water chemistry must have been substantially different. I've heard estimates that, for example, the pH of the oceans, the acidity of the ocean was anything from about 5 to 10, which roughly translates to we have no idea. And then this final thing that a lot of people don't think about, we have a 24-hour day. We're used to that. But it turns out that the rotation of the Earth is slowing down over time, and this is because of a frictional interaction between the Earth and the Moon. This is something actually one of Darwin's sons figured out. And so as time goes on, the rotation of the Earth becomes slower and slower. And if there are any students in the audience, I quickly point out this is not going to help you get through your final exams this year. Day length is not going to be substantially longer in our lifetime, but slowly over time it becomes longer and longer. So again, if you run the clock backwards, when life arose, the day length may have been about 16 or 17 hours. So that's surely going to affect how organisms go about their business. So what we've seen is some major environmental changes. So let's start again. There's the sun. And so I'm going to argue that in the beginning, what organisms really had to focus on more than anything is not competing with their neighbor, but dealing with a physical environment. And when I say physical, I mean the chemical environment as well. So this struggle for existence was against the physical world, and this is still the number one thing that organisms have to worry about. The other thing they have to worry about is entropy. I was delighted that Eric mentioned Schrodinger and the second law of thermodynamics. We would be breaking down if you have a dead organism. Ultimately, they decompose because the energy is dissipating. We're following the second law of thermodynamics. How do we cope with the fact that we would break down? Well, the answer is that we eat. We like to eat because it tastes good and so on, but what we're really doing is fighting entropy. So the next time you feel like having a second piece of cake for dessert, or the second helpings on the potatoes, you just say, I'm fighting entropy. This is what I'm supposed to be doing, right? Okay, so we're fighting entropy and we're dealing with physical and chemical environment. Secondarily, you have to worry about your neighbors, and that's not to say that that competition doesn't go on. It's tremendously important, and the biological aspects are tremendously important of organisms. But again, what I'm going to argue is the number one thing we have to worry about is the environment. So let's put it really bluntly, are we talking about physical environment, or are we talking about natural selection? And I'm arguing that certainly both occur, but the first of those, the physical environment, is what tends to get lost in the cracks and is tremendously important, particularly if you're going to look for life elsewhere in the solar system. One of the ways we can approach this is by looking at what is needed for life. And this is a slide that, this sort of slide you might have seen before. We need a couple of things. We need liquid water. We need biogenic elements. That means that we need things like carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, a source of energy, and we need time. And I've already ridiculed that to some extent. We don't really know how much time we need. We know that life didn't arise instantaneously, but we don't know if it's Columbus Day weekend or if it's 500 million years. But we know it takes some sort of time. And so these are sort of the usual things you see on the slide. And so now let me give you something just a little different take on this. What do organisms really need for life? Well, unless you're doing some sort of Star Trek virtual reality, the number one thing is they need a body. They need a physical presence. And I'm going to argue that a lot of what follows in life is because they need a physical body. I'm going to argue further that this physical body is likely to be based on organic carbon, and it doesn't matter whether it's planet Earth, planet Mars, or some completely yet undiscovered planet on the edge of the universe. It's likely to be based on organic carbon, and therefore the top priority for organisms is finding organic carbon and putting it together in a body. In order to do that, you have to fight entropy. So yes, it's a good idea to eat your dinner. And you also have to do other sorts of things to survive. But the number one thing is to have this body. Otherwise, everything else falls by the wayside. Now, why do I say the carbon is so important? I'm doing this as a straw man because I know there's going to be someone in the audience who's going to say, what about silicon? Well, the fact is the carbon is the fourth most common element in the universe. There's carbon up there, nice little molecule, capable of forming a vast array of compounds from methane to DNA. Silicon can form interesting compounds too, but it pales in comparison to the complexity of carbon. Every college teaches courses in organic carbon, in other words, organic chemistry. I don't know ones that teach whole courses on silicon chemistry. It's just not as interesting. And the fact is we live on a large silicate rock, and we're not based on silicon. If anyone would be based on silicon, we would be certainly good candidates. But I think to me what's been an even stronger argument is the fact that colleagues of mine at NASA and elsewhere have looked out into the interstellar medium among the stars, and they find a very similar organic chemistry to what you learn about in a class in college or in high school. So the language that we need to learn about, for those of us who went through all the pre-med classes and so on, the language that we have to learn about in school is not just the language of getting into med school, it's the language of the universe, which makes one start to feel that perhaps that is the universal language of life. And to me, that is absolutely stunning thought. And if nothing else that you remember tonight, that's certainly a good take-home message. So we said that organisms need a body. If you're going to be based on organic carbon, water is an awfully good solvent. And so then you're really finding that almost everything else falls from that, organic carbon and water. And almost anything else you can argue from life comes from there. Obviously, organisms also have to deal with a changing environment. Again, the word environment comes in. You have all sorts of ways of doing that, physiological, morphological, genetic, and so on. But the fact is your body has to stay intact, so it has to deal with the physical environment. You have to leave offspring. Those offspring have to leave offspring. As people say, the only point in having children is having grandchildren. And then you need some sort of continuity. And again, this has to do with the idea that grandchildren are a great thing. Okay, so if we're going to look at the physical environment in life, it's really instructive to look at the actual limits of life. And this is what I do to some extent. It gets me to exotic places on planet Earth. And so what I'll do is to show you a few slides to sort of give you an idea that the envelope of life, as we know it on planet Earth, is far broader than we would have imagined 10 or 15 or 20 years ago. And I bet it's going to be even broader in another 10 or 20 years. And therefore, this gives us an idea of what the range of conditions where life could form on Earth and elsewhere becomes broader and broader. And it really enriches our definition of life. So what we're going to do is turn to these organisms that are known as extremophiles, extremis being the Latin for living on the edge, phile meaning love. So these are organisms that really like to be on the edge. Of course, not all of them, love it. It's not like I interviewed them and said, hey, do you like living in high levels of radiation? But the fact is they can do it. Love is sort of a subjective term. You're not going to want to really read the rest of this table in great detail, so I'm putting up a simplified form just to give you an idea of some of the physical and chemical extremes that we'll talk about. Temperature, that's a very easy one to deal with. Radiation, pressure, desiccation, salinity, acidity, pH, acidity, alkalinity, oxygen tension, chemical extremes, even living under a vacuum or with electricity. And I show you this to give you an idea that there are plenty of organisms that can do all of these sorts of things. So let's go talk about a couple of these, maybe in a slightly different way than what you're used to. Let's talk about temperature for a moment. Now, it turns out that there are a whole lot of reasons that organisms don't like to live at 200 degrees Celsius or minus 200 degrees Celsius. We like to live days like we had today in Boston, which was, just absolutely lovely. You're talking about, sort of low to mid 20s Celsius. Why do we like that so much? Is it just something, an idiosyncrasy of us? Is it because we've evolved to live in New England, or is there something about life? And I'm going to argue there's something about life. For example, the solubility of gases in liquids changes dramatically depending upon the temperature. And for those, I know there are a few kids in the audience, what I suggest you do is tonight or tomorrow take 2 soda cans and put one in the freezer and put one in hot water for about an hour. And then either go outside with them, wait till your parents aren't home, or go into the bathtub and open them. And I can assure you that one of them is going to go pow, and one of them is going to go bzz, and the one that goes bzz is going to be the cold one. And that's because the solubility of gases is so much better at cold temperatures. So you think, cold, that sounds great. The only problem with really low temperatures is that water freezes. If you shrunk yourself down to the size of, say, a mitochondrion, or even as tiny as an atom, you would see that when water freezes, it forms ice crystals, and these would look to you like swords that would start ripping through cell membranes and forming an awful mush. So you don't want to be in a situation where there are ice crystals forming, but you don't really necessarily want it too hot. So if you get it too hot, you start to break down compounds like nucleic acids and chlorophyll and proteins and so on. I tell my kids, you can't unfry an egg. Once you denature proteins with heat, that's all she wrote. If anyone can invent an egg unfryer, I think you're well on your way to, if not the Nobel Prize, something else equally good, no doubt. Enzymes have optimum temperatures for activity. So we really are constantly dealing with temperature. And this just brings home the point. All right, now, saying all that, you would think everyone lives at these mid-temperatures. This is about where we were today in Boston. But the fact is that there are organisms that can live well above that temperature, well above the temperature that you would expect any reasonable organism on the basis of what I just told you to live. In fact, we found archaea now that live at 113 degrees centigrade. You would have not only a boiled egg, you would have a boiled egg that you probably wouldn't want to serve for dinner. It would be so nasty. There even have been reports of organisms living at 121 degrees centigrade, but that hasn't been confirmed. There have been organisms that have been reported to be metabolically active at a few degrees below zero, tons of those, fish with antifreeze and so on. There's a report of a Himalayan midge, just bouncing around at minus 17. I have no personal interactions with Himalayan midges, so I can't verify that. However, like I'm sure many of you in the audience, I went to March of the Penguins last week, and it doesn't take a rocket scientist. I love saying that when I work in NASA. It doesn't take a rocket scientist to know that there are lots of organisms that live below 0 degrees. And when I say this in an audience of so-called professionals, what I hear is, yes, but they're cheating. What do you mean cheating? Organisms can live at these low temperatures. There's not this rule book, well, it doesn't count if you happen to grow feathers and have warm blood. It's just one more adaptation. So if you start to look at that, we realize there's an enormous range of temperatures that organisms on Earth can be active in. And if we start to look at where they can at least survive, you realize that we can broaden that quite a bit. All you have to do is think about things like in vitro fertilization, sperm banks and so on, to realize that even body parts of humans can deal with liquid nitrogen temperatures. This gives you an idea of what life looks like at these very high temperatures. This is Octopus Springs, which is one of those meccas for microbiologists in Yellowstone. Yellowstone is at a much higher elevation, around 6,000 to 7,000 feet, where Octopus is, and so water boils around 92 degrees. So when you have something over 95 degrees centigrade, it's already boiling. There are organisms alive in here in this source. As the water starts to cool down, you're going below 92, but not a whole lot. Here in this outflow channel, it's about 83 degrees centigrade. And you're welcome to stick your hand in something 83 degrees centigrade. I slipped once in this little outflow channel, and it's only a centimeter deep, but you've never seen anyone take a boot off so fast in your life. It is very, very hot. And yet there are plenty of organisms that live there. I don't know if you can see these sort of pink streamers called thermocrinus. They're perfectly happy at those temperatures. If you start to cool off even a little more, 65 degrees Celsius, that's still awfully hot. You see very rich microbial mat communities. Here you have a channel that's about 75, 76 in the center, and so you don't see any green because chlorophyll breaks down at those temperatures. But the instant it's below about 73, you have chlorophyll able to stay stable, and you have organisms that are photosynthetic. So you see this beautiful zonation. So you can see that there's plenty of life that can live at these high temperatures and do very nicely. And conversely, besides all the penguins, at low temperatures you can see things like, for example, snow algae, things that are called watermelon snow. I took this picture when we did a field trip to Lassen last summer. They must have had quite a bit of snow because here we were in July and there were huge packs of snow. The snow was tinged pink, and the pink color comes from these green algae that have a lot of red carotenoids, which protect them from the sun. I'm not colorblind. These are green algae with a lot of red carotenoids, and you'll see in other pictures, organisms that have to protect themselves from high amounts of radiation, microbes, usually produce a lot of carotenoids to protect themselves. Let's look at pH for a second. Probably all of you are thinking, oh, what was pH again? I remember learning about that. pH is very simply the concentration of hydrogen ions, and so the lower the pH, the more acidic it is because you have a higher concentration of ions. At the high pHs, you have a much lower concentration. Neutral is considered 7. The ocean is about 8.2. So when you're getting to 10.5, you're talking about soda lakes in Africa. Plenty of organisms from a diversity of taxa live there. It's very hard to keep something at pH 12 in the lab, particularly a culture medium, but I've been assured by colleagues who work in some of these lakes in Africa that they've measured the pH at about 12. There are organisms there, and therefore there are organisms that live at these pHs, even though they haven't taken them back to the lab. On the other extreme, you're starting to deal in here with things like lemon juice, battery acid, and below, and yet we're finding more and more organisms that can live down to pH 0. Believe it or not, you can go below pH 0. You now can buy fancy pH meters that will go below pH 0. And I'm sure it's only a matter of time before someone reports that they found an organism living below pH 0. Again, here we are in Yellowstone. This is a boiling acid mud bath at about pH 0.5, and yet this is home for Sulfolobus, which is a bacterium. Not my idea of home sweet home, but this is where this organism is specialized in living. Another sort of acid area in Yellowstone, this is in the Norris Geyser Basin region. This nice little stream here is about pH 2.5, nothing like 0, but I mean, hey, that's way down there. Again, remember the ocean's 8.2. Absolutely covered with this unicellular red alga called cyanidium. Again, I'm aware of the fact that that looks green, but it is a red alga, trust me. This micrograph that I took is not a culture, that's a field sample. So it gives you an idea of the density. These organisms are able to grow in the lab at room temperature. They can grow at neutral pH, but they're lousy competitors. When you go out into nature, they're up there at around 40 to 50 degrees, and they're at these very low pHs because that's where they make their home. That's where they're better than everyone else. And there's my daughter a few years ago. This is also the same pH, but here this area is not fed by hot springs in a continuous sort of way. There are little tiny mini geysers coming out, but most of this mat is exposed to temperatures that are much closer to ambient, and so you don't see as many cyanidium. You see this area just absolutely covered with zygogonium. You know, once again, this is a colorblind situation. The zygogonium looks sort of purplish to you. It's because as it gets older, it makes purple pigment to protect itself from the sun. So again, just the difference in temperature means a complete difference in community. Salt is another area that's very difficult to live in, high salt, and yet there are organisms that, as you can see, oops, I don't know if I'm getting this at all. This is when I always say in the lecture, I'm not in the technical end of NASA. I'm not responsible for the shuttle. I'm only a biologist. Anyway, you can see in the upper left panel, there's salt crystallizing the side of the salt pond where we used to do some work in Mexico. And there are organisms living there, those reddish things right on top of solid salt. There's my wonderful technician, Dana, getting a sample from San Francisco Bay from the Cargill Salt Company. Again, red because of the protection from the sun. There's a spot up in the Andes where we're starting to do some work. Again, very high salt concentrations, very high levels of carotenoids, organisms particularly adapted to this environment. Along with the very high salt, these organisms are also very often radiation resistant and resistant to desiccation, loss of water. Remember, water is tremendously important for any organisms. Bringing up the idea of radiation, here's a pond. I'm sorry I didn't show you an overall picture, but this is about 13-hour drive north of Adelaide in Australia. This is officially the outback, Paralana Springs. Why would anyone drive 13 miles north of Adelaide to go visit this stream? Well, that bubble there is not just any ordinary bubble. It's full of radon, radium, and uranium. This is a few miles from a uranium mine. So these organisms are getting whacked with enormous amounts of radioactivity from down below. From up above, they're getting hit with that really strong Australian sun. So they're having to deal with very high levels of radiation, yet, I mean, you can see here from the green and the brown and so on, there are many organisms that seem to be able to do that. And these are some of the things we're studying. We do know that there are organisms like Deinococcus radiodurans that can live under such high levels of radiation, their DNA actually fragments, and then they put it back together like a puzzle. The reason that we worry so much about radiation, particularly ultraviolet radiation, is because our nucleic acids and proteins have peak absorptions in the UV, around 260 and 280 nanometers respectively. So anytime we're anywhere near these levels of radiation, this range in the solar spectrum, it's danger, it's problem. And that's why we worry so much about the ozone hole. We worry so much about getting more ultraviolet radiation in anywhere near that range. And this would be true of any organism in the universe if they're based on organic carbon. So again, a lot of what I'm telling you will follow from the idea that organisms are based on organic carbon and using water as a solvent. Here's another place where we started doing some work last November, the Altiplano. This is up right across the border into Bolivia from Chile, up in the Andes. We're up there at about 14,000 feet. So the level of oxygen is pretty low. Take my word for it, you feel completely winded. The level of UV is very high. And therefore, you've got these organisms up there that can survive the low oxygen, the high UV. And on top of it, there are all sorts of weird chemistries, like here, these boiling mud baths with sulfur deposits, so no doubt they're extremely acidic. I hadn't expected to run into them, so I didn't have anything to sample, but I will when I go back this November. So you have these organisms that are having to deal with very stressful, bizarre situations. Taking you a little closer to home, I did this experiment with a master's student of mine a few years ago, very, very simple-minded, where we put some yeast cells on the roof. Again, we live in the Bay Area. We live not too far from San Francisco. This was at the end of March. So it's, roughly comparable, I would say, to Boston, sort of mid to end of May. And what we did was we took some of the cells and we put them under UV transparent plexiglass. That's the UVT. I'm sorry, Eric, I think this is sort of dying. The UVT is just UV transparent plexiglass. The Mylar has the UVB part of the spectrum taken out, and the OP3 has knocked out all of the ultraviolet radiation. And what you can see there is that the organisms who were exposed to the normal solar radiation, this is just on the roof of our lab, nothing fancy, grew substantially slower than ones that were not exposed to UVB, and even slower than ones that were not exposed to any ultraviolet radiation. So this is a very simple-minded experiment. So then you can start extrapolating to what it would be like if they were out there every day, what it would be like in the middle of the summer, what it would be like in Bolivia, what it would have been like on early Earth, and certainly what it would be like on a place like Mars that has no ozone shield whatsoever. So you can see that radiation is going to control a lot of what we do every day. In fact, I have a lot of data, which I'm not going to bore you with tonight, showing exactly what times of day we start to have to shut down our DNA and so on because we're having to deal with damage from the sun. I'm developing a vision where I really think much of the world outside is cued into the sun, and it's every day. Now, tied in with the sun and radiation is oxygen. Oxygen is the one environmental extreme that we consider absolutely normal because we've evolved to live in an environment with 21% oxygen. We're perfectly happy here, and we don't think of ourselves as extreme. We tend to think of ourselves as normal. But I'm going to argue that this is actually one of the worst environmental extremes, and therefore we would conclude that we're extremophiles too. Well, oxygen, is a great thing. I have nothing against aerobic metabolism. I do it every day myself. It's a wonderful thing. The reason it's so wonderful is it's 18 times more efficient in breaking down glucose than anaerobic metabolism. I'm sure I wouldn't be this size. None of us would be here if our ancestors hadn't figured out how to use oxygen. But that is a very risky strategy. I just showed two organisms there that are aerobes. The one on the left is playing around a little with being anaerobic, but he's a champion bagpiper, so he knows better. He knows that the way to go is to be an aerobe. But the problem with being an aerobe is it's extremely dangerous. And the reason I say that is oxygen's all very nice and water's very nice, but there are a whole lot of reduction products between oxygen and water that are not so nice, like superoxide, anions and hydrogen peroxide, hydroxyl radicals, which I have circled there in the yellow, are the nastiest of them all. These intermediates can break down your membranes, they can destroy your DNA, they're nasty, and so you're really literally playing with fire when you start becoming an aerobe. The quote that I remember and I'd like to throw out is that there are estimates that by living and breathing, that your average couch potato every day has 17 hits of oxidative damage in every cell in every cell in their body that needs to be repaired. Now, that's being a couch potato. That's not even including getting up, having breakfast, going swimming, or anything else. So this is something, again, we're not aware of, but our bodies are acutely aware of. Oxygen is dangerous. It's a great thing, but we better be prepared to deal with it constantly. And again, as I say, I do a lot of work out in the field trying to figure out what organisms are doing in their physical environment. And I got the opportunity to show one data slide, so I will show it, where we've taken some of these microbes that live in this case, Nymph Creek in Yellowstone, and looked to see what would happen if we started increasing the level of oxidative stress. And we find that with a little extra oxidative stress, there's actually an increase in mitosis, and that's what you see in the top there. The cell numbers go up. So what we think is these cells are trying to outrun the damage by making a lot more offspring. And you can see from the lower two slides that, in fact, they're feeling the damage, but at these low levels, they're trying to outrun it. Now, at the higher levels, they shut everything down. They try to figure out how to just fix the damage to survive, and if you give them enough, of course, they go to algal heaven and all that. And so let's try to put this whole big picture together, at least for UV and oxygen, because I've given you so many variables it would be very difficult to graph. We got the formation of the Earth down at the bottom there at about 4.5 billion years ago. You've got the oldest rocks coming in. We know that there's water very early on. We don't know if there was life because of the bombardment period, but we have oxygenic photosynthesis taking off fairly early. All sorts of organisms coming about, huge variation in the microbes up to near the Cambrian explosion, probably a little bit more. So most of the history of the Earth has really been dominated by microbes. You see at the very top things like multicellular organisms. You see starfish there, dinosaurs. At the very peak of evolution, you see the NASA logo, because that's how I get paid to put that in. So anyway, you see all of that. And at the same time, superimposed on it, you see a change in our atmosphere. We've always had enough CO2 to protect ourselves from the very dangerous levels of UV radiation, everything below about 200 nanometers. But as time went on and as the oxygen levels rose, thanks to cyanobacteria, algae, and plants, the UVB portion of the spectrum started to fade off, and so we have really very little left. So all of these organisms, all this evolution that went before was going on in this very harsh ultraviolet environment, plus all the problems with desiccation and salinity and pH and everything else we've talked about. And then if things weren't bad enough, like I say, the day length has changed. So our very earliest ancestors were having to do all these things in a very rapid period of time because they're dealing with 16-hour days instead of 24-hour days. So let's just conclude by looking and seeing what this might mean for life beyond Earth. I gave a lecture yesterday in the Midwest, and so I'd leave this slide in. This is Iowa. Iowa's the moon, Jupiter. Anyway, it's great. I actually gave my students extra credit last year for coming in with astrobiology cartoons, and that's sort of a no-brainer way to get extra points. So let's look just simply at our inner solar system, because as I argued, I think that we would see actually the same thing in the rest of the universe, and I don't think it's because of a lack of my own imagination. I think it's because we believe that life would be based on organic carbon and water. If you look right in close to the sun, you see Mercury. Actually, you don't see it because it's so tiny, and I tried to put these in relative size. Prospects for life on Mercury are rather dim. One side of Mercury is constantly facing the sun, and it is, really nasty. It's the place from hell. The other side is extremely cold. There's probably 2 meters worth of, sellable property in between the two, but the waterfront view is rather grim. So we're going to move on from Mercury to Venus. Venus is our twin that went bad. It had a runaway greenhouse. So at this point, it's extremely inhospitable. It could have had life early on. At this point, it's got serious amounts of acidic atmosphere, acidic vapors, and some water vapor. Now, there are people in the last few years who have seriously suggested there are organisms living at a certain altitude in the clouds above Venus, and they have some spectroscopic data. This is not widely accepted, but that idea is out there, and I'd be remiss not to at least mention it. The third rock from the sun, of course, is planet Earth. We know that there's plenty of life there. So let's move on to the little red dot. That's Mars. NASA's been using the approach of follow the water. We do know there's plenty of water on Mars. At this point, we don't think it's liquid. We do know there's plenty of ice in the polar caps. There are people who firmly believe there may be hydrothermal systems, in other words, water systems beneath the surface on Mars that could, in fact, contain life. They're protected from the ultraviolet radiation and so on. I've showed you organisms living in evaporites. We now know that there are evaporites on Mars. These organisms would be protected from the sun. There wouldn't be a lot of action, but there'd be protection. And there are people who believe that there could be small pockets of water on Mars today, and I'm very flattered to be asked actually to propose for a mission in 2011. So, maybe I can come back in 2012 and give you a firm answer. But I think that there certainly is a possibility. And so moving from there, we've got Jupiter. Europa is a moon of Jupiter. We do know that there's liquid water beneath the surface. It's a really likely place for life. The bad news is it's expensive. It takes a long time to get there, and oddly enough, NASA is not really big on large, expensive missions at the moment. But we keep our fingers crossed, and it's been back and forth on whether we have a GMO mission, the Jupiter Icy Moon Orbiter. Next to there, you've got Saturn. Titan has been in the news a lot this year. It's an organic chemistry lab par excellence. Tons of organics, other solvents besides water, but extremely cold. So this is really more of a frozen chemistry lab. I tell the students, no reputable scientist suggests that there's life on Titan today. And then Francois Roland from the French and collaborating with ESA says that you can't completely rule it out. So there you go. But the fact is that what we've done is we've taken all these ideas that I've given you about the physical environment of life, applied them to our solar system, and again, beating this over and over, I think that we could apply the same sorts of things to the rest of the universe. And that just says what I just said before. So what does this mean? What it suggests is that organic chemistry is the language of life on Earth and appears to be a language of chemistry in the universe. And so therefore, if we replay the tape, there are going to be certain things that will happen again. We will have organisms needing organic carbon. Some will figure out how to make their own, like photosynthetic organisms do on the Earth today and other autotrophs. Some of them will figure out the cheap way to get a meal is to eat the organisms that make their own organic carbon, and so on and so forth. And you have a repetition of this kind of food web and these kinds of organisms. And so the implication is that we don't bother to look for truly exotic life forms. So that pretty much is concluding what I have to say. There are limits to life, and they're connected with the fact that we're based on organic carbon and liquid water. And the number one thing that we have to deal with is having a body that has to have some sort of permanence in face of entropy in the physical environment. This envelope for life is far beyond what we ever imagined it would be. And that some of these adaptations to living then on the edges are very simple. I didn't discuss that in any detail. Some of them are very complex. But the point is that for every one of these, we see multiple organisms from multiple taxa having figured out how to make it in these environments. So what we're not saying is that, yes, there are these organisms from Bolivia that are found on Mars or anything like that, but we're just saying that there's nothing about life per se that precludes it from living in those environments. And finally, we're finding an increasing number of habitats where this could work. And so before I hand this over to Jim, I'm going to finish with this slide, that the picture's pretty bleak, gentlemen. The world's climates are changing. And I point out that's the environment. Number two is the mammals are taking over, competition. And then we have the brain the size of a walnut, and that's biology. And that's sort of where I feel right now. So thank you very much, and pass it over to Jim.
Very good.